Howdy, welcome to Math 153, Elementary Statistics. My name is Lance Curtis, and I am going to give you the lecture for sections 9.4 and 9.5. As you can see, in this lecture we're going to finish up chapter 9, starting with looking at matched pairs. So we're going to test the mean between two dependent samples. So when you're dealing with two dependent samples, there are methodologies for testing hypotheses and constructing confidence intervals. Remember what we discussed in the previous lecture about independent versus dependent samples. Sample data is dependent if there is some relationship between the two samples. So there is one member of the first group that is related to or connected with a specific member of the second group, and you can do that for each member of each group. That's dependent samples. So what we're going to do is look at both hypothesis testing and constructing confidence intervals. And as we've seen before, when you're looking at the mean value, the confidence interval is just as reliable as using a p-value or a critical value when testing a claim with hypothesis testing. So we should be reaching the same conclusions regardless of whether we're using hypothesis testing or confidence intervals. And we're going to be using the t-distribution as a reasonably good approximation. There really is an exact procedure for dealing with dependent samples, but the t-distribution approximates what's going on reasonably well, and so this is what we're going to be using. Now, if you want good experimental design, the question often arises, which is better? Should we plan on using independent samples or should we plan on using dependent samples? And the answer to that question is usually you want to use dependent samples with paired data. It's generally better than two independent samples. And the reason for that is that when you have two independent samples, you have much more variation overall than if you have two dependent samples, because the relationship between the members of each grouping is going to put some sort of control on the variation. Because if there's a variation in the first sample when you have dependency, then that's going to affect the variation in the second sample, because each member of each sample is related to a corresponding member of the other sample. With independent samples, you can have all sorts of variation. There's no real relationship between the samples, and so therefore you can have a lot more opportunity for overall variation in all of your data than if you were dealing with strictly dependent samples. And so for this reason, you want to try to design experiments so that you have dependent samples with paired data. Sometimes you can't get away from it. The nature of what you're looking at, basically, you're going to have an independent sample, and that's okay. I mean, we saw in the previous lecture how to deal with that. But overall, if you do have a choice between designing an experiment with independent samples or dependent samples, you want to go with dependent. Now, our requirements for this test there's a few of them, and they have to be met. The first one is that the sample data are dependent. Typically, the methodologies we've been using up till now have required independent data sets. But since we're dealing specifically with dependent data, it's not surprising that we're not requiring our sample data to be independent. Rather, we are requiring them to be dependent. Samples must also be simple random samples. That's typical. And another typical requirement, either the number of pairs of sample data. Notice not the number of sample size. We're not looking at sample size. We're looking at the number of pairs of sample data has to be greater than 30, or the respective populations are normally distributed. Again, we can get away with not having a normal distribution for the population if the sample size is greater than 30, because central limit theorem comes in and says if our sample size is greater than 30, we can use the normal distribution to approximate. Of course, if we already have a normal distribution to start out with, It doesn't matter what our sample size is. We also use some special notation when working with matched pairs. So just as we saw when we're working with independent samples, there are some conventions that we need to be aware of when dealing with matched pairs of dependent data. So the first one is we're going to use the lowercase letter d to represent the individual difference between two values of a single matched pair. So for example, if you have, say, the age of a husband and the age of wives, then the age of the husband minus the age of the corresponding wife, okay, will be the difference d between the two values of that single matched pair. Then you'll take another husband and another wife, and that's another d value. So there's a separate d value for each matched pair within our data set. Mu sub d is then going to be the mean value of the differences for the population of all matched pairs of data. So we're going to take the differences for each of the matched pairs and we're going to average those differences out. That's going to give us mu sub d. D bar is the mean value of the differences d for the paired sample data. S sub d is a standard deviation for the differences d of the paired sample data. So this is, again, this is because it's lowercase, we're talking about the sample, not the population. And of course, n represents the number of pairs of sample data. The sample size for each sample is going to be the same. It has to be if you have paired data. So when we go to test our claim about our hypothesis, many of the same conventions that we used previously to form our hypothesis and test the claim are going to hold true, just like we'd had with independent samples. We do, however, have a slightly different test statistic, and here it is. T equals d bar minus mu sub d all over quotient of S sub d over square root of n. Similar in form, but slightly different because, again, we're using values that are specific for matched pairs. As always, you can use p-values and critical values with a t-table, or you can use software to evaluate your hypothesis test. You can also construct confidence intervals to evaluate dependent sample claims. So here's our general form for our confidence interval, d bar minus e, d bar plus e from our lower and upper limits respectively, and it's all centered around mu sub d. Of course, e is going to be the margin of error, and that's defined by this equation here. We get our critical t-score and multiply it by S sub d over the square root of n. This gives us our margin of error. So let's look at an example. We've examined before the heights of presidents of the United States against their electoral opponents. What we haven't done previously with a specific example is to say, okay, so we're going to compare the two groups and say, is there really a difference in the height between the two presidents? Excuse me, between the two candidates? So you have a candidate who wins, who becomes president, and then you have the electoral opponent who loses the election. Is there a difference between the heights of the two candidates? So here we have, listed in the table, we've selected 5 at random presidents of the United States and their corresponding electoral components, and then we measure the heights in centimeters of each of these individuals, and you see them listed in the data table here. So now we're going to use a 5% significance level to test the claim that the differences have a mean greater than 0. In other words, because the difference is greater than 0, that means that the presidents are going to be taller than their opponents. So first we check to make sure our requirements are met. So the samples are dependent because the values are paired. The pairs of data are randomly selected. We have 5 data points, and 5 is far less than 30, so we should check for normality. So if we take our 5 data points and put them in a QQ plot, here's what we get. Doesn't look anything too crazy going on here, so we're going to say, yeah, we've got normal distribution for a population, and therefore appears that our requirements are met. Now we're going to form our hypotheses. Remember, we first start by representing the claim symbolically. Well, what is our claim? Our claim is that the mean height of U.S. presidents, which we're going to say is mu sub 1, is greater than the mean height of their electoral opponents, which is mu sub 2. This means that mu sub 1 greater than mu sub 2. But that's the same thing as writing mu sub 1 minus mu sub 2 is greater than 0. Again, I just took this mu sub 2 and we subtract it from both sides. That brings it over to the left side. So now I've got both of my variables here on the left, and I have a 0 there on the right. That's the algebraic equivalent way of writing the claim symbolically. Now, because we're talking about dependent data here, we're going to switch out from saying, instead of saying mu 1 minus mu 2, we're going to say mu sub d. We're going to use mu sub d because that is the difference between the means of the two samples when you're talking about dependent data. So we're going to substitute that in and say mu sub d is greater than 0. This then is a symbolic representation of our claim. Now we're going to write the null hypothesis, and as always, the null hypothesis is a statement of equality by definition. So we're going to say mu sub d equals 0. That's our null hypothesis. Then the alternative hypothesis will again generally reflect the claim. Here we just take the claim and just make it our alternative hypothesis, because notice there's no semblance of equality here in our symbolic representation of our claim. So therefore we can just extract it out, take it as our alternative hypothesis. Before we go to evaluate the test statistic, we need to assemble some summary statistics. So here I have a table that we saw previously, but I've added another column where I've calculated the differences between individual matched pairs. So these are my D values here. So 189 minus 170 gives me 19. 173 minus 185 gives me negative 12, so on and so forth. Then what I need to do is I need to find D bar. Now D bar is going to be the mean of the differences. So if I take these differences and I average them out, as you see here, I get 3.2. This then, 3.2 is my D bar value. I also need to find sample deviation of the differences. So I can do that by applying the general formula for sample standard deviation, which you see here. So I take all these different difference values, subtract it from the average or the mean of those difference values, which is D bar, square those differences, add them up, divide by 1 minus the sample size, and I come out with 11.4 for S sub D. These two values then allow me to then calculate my test statistic. So let's go do that. Here's the general form for the test statistic. I'm going to plug in what I know. So D bar, as we just calculated, 3.2. S sub D is going to be 11.4, as we just calculated. Our sample size is 5, so that goes in for N. And then notice how mu sub D is equal to 0. Again, we're operating under the assumption that the null hypothesis is true. Well, what is the null hypothesis? The null hypothesis is that mu sub D equals 0. Therefore, I'm going to substitute 0 in for mu sub D. Punch all this out on my calculator, and out comes 0.627668. Now, our method is based on the t-distribution, so we can take this test statistic and use it to find our p-value. So here I have my t-distribution, 4 degrees of freedom, that's 1 less than the sample size. I put in my test statistic, and out comes the area, which is my p-value, 0.2821. Then I'd compare my p-value with the significance level of 5%, and I find that the p-value is much greater than 5%. That means the area represented by the p-value is larger than the area represented by alpha, or the critical region. So I can't fit the p-value into the critical region. I'm therefore outside the critical region, and therefore I fail to reject H0. We can reach the same conclusion by comparing the test statistic with our critical value. So if I use the same t-calculator to figure out, okay, what's my critical value, put in the area for my alpha, then I get the critical value come out to 0.13. And if I compare that value with the test statistic, I find the test statistic is smaller than the critical value. So, because I'm smaller than the critical value, I'm actually outside the tail that's represented by the critical region. Therefore, I'm going to fail to reject H0. So either way, we reach the same conclusion. There is insufficient evidence to support the claim that U.S. presidents are taller than their electoral opponents. We can also use a confidence interval to come to the same conclusion. As I mentioned previously, when you're dealing with the mean value, confidence intervals are just as reliable as using a p-value or a test statistic to evaluate hypothesis tests. First thing we do is find our margin of error E. So here's our standard equation for finding margin of error for matched pairs. I substitute what I know. So I had to go find the critical value for my t-table or software. That gives me the 2.7764. And then the 11.4 we calculated previously for S of D, and then 5 is the sample size. Punch all this out in your calculator, and out comes 14.15. This is our margin of error. I then take and substitute into the general form. So here's the general form. I substitute what I know. My D bar is 3.2. The error that I just calculated, 14.15. And then I'm going to add it on the right, subtract it on the left, and that gives me my lower and upper limits for my confidence interval, negative 10.95 and 17.35 respectively. This then is my 95% confidence limit. Now, because our confidence interval includes 0, it's possible that the mean difference between the samples is going to be 0. And if the difference between the means is 0, then that means there's no difference between the samples. And since the samples represent heights of U.S. presidents and their electoral opponents, we reach the same conclusion we did before, that there doesn't appear to be a difference between the mean heights of U.S. presidents and their electoral opponents. That brings us to the end of the 4th section in Chapter 9. So now let's tackle the last section, talking about two variances or standard deviations. So when we're evaluating two population variances or standard deviations, we're going to be using what's called an F-test. And the F-test is so called because it's based on the F distribution. Now the F-test is very sensitive to departures from normality. So our samples must be normally distributed. That's going to be a requirement that we look at. But before we examine that, let's take a look at the F distribution, because we've never actually seen this before in any of the previous chapters in this course. So we're brand new to the F distribution. Let's get an introduction. Remember that when we were testing claims about one population standard deviation or variance, as we did in Chapter 8, we used the chi-square distribution. Now that we're looking at two population standard deviations or variances, we're using a different distribution called the F distribution. The F distribution is very much like the chi-square distribution, but there's some minor differences that are very important that make it more applicable for testing two population standard deviations or variances. First, as you can see, the F distribution is skewed, as statisticians say, to the right, because they're looking at the larger tail of the distribution. I, as the engineer, look at this and say it's skewed to the left because that's where all the data is. But, okay, we understand that. F distribution skewed, however you want to say it, even more than the chi-square distribution. Okay, so the chi-square distribution was skewed. The F distribution is skewed even more. Furthermore, the density curve, just like the chi-square distribution, never falls below the horizontal axis. So all the values you get from the distribution are going to be positive. They will never be negative. Now, we notice that with the chi-square distribution, we have one degree of freedom value. The F distribution differs significantly from the chi-squared in that it has 2 degrees of freedom value. So there's a DF1 and a DF2, not just DF. This is what makes the F distribution more applicable for testing two population standard deviations or variances because we have a separate degree of freedom value from each sample that we're examining. So, requirements for the F-test. The first one is that the populations are independent. Second, simple random samples. So far we've seen pretty much standard fare. Both the populations must be normally distributed. This is a pretty strict requirement. We saw this before when we were looking in Chapter 8 of the chi-square distribution, testing one population variance or standard deviation against a claimed value. But now we're looking at 2, we have the same requirement. Both the populations must be normally distributed. If we had this requirement because of the skewness of the chi-square distribution, you can surely bet that we're going to have it with the F distribution, since the F distribution is skewed much more than the chi-square distribution. As we've seen previously, we're going to have some special notation when dealing with this particular area of hypothesis testing. So, whereas before we were looking at subscripts 1 and subscript 2 to represent different groupings. So one of the samples would be sample 1, one of the samples would be sample 2, and sample 1 was typically the one that was mentioned or described first. Here, when we're looking at the F-test, the subscript 1 goes with those values that correspond with the sample having the larger variance. Subscript 2 then denotes sample statistics from the sample with the lesser or lower variance. This is an important distinction. So when you see N1, it doesn't necessarily mean that this is the sample size of the first sample. It means it's the sample size of the sample with the larger variance. And so N2 would mean that this is the sample size of the sample with the lesser variance. And the same pattern follows for the other variables, S, sigma, what have you. So our test statistic is going to be an F-score because we're basing it on the F distribution. And here's how we calculate it. We take the variance from the sample with the larger variance and we divide it by the variance from the sample with the lower variance. So we take the variances of the two samples, take the higher one, put it on top, take the lower one, put it on the bottom, divide it out, and that gives us our F-score. The numerator has degrees of freedom df1. Okay, again, because this is the first sample, and it's the first sample not because it's described first in the problem necessarily, but because it has the larger variance. Likewise, the denominator has degrees of freedom df2. Remember that the lowercase letter s denotes the larger of the two sample variances. There really should be s squared, since the lowercase letter s is sample standard deviation. So it really should be squared. I'll have to make a note to correct that. So s squared denotes the s squared sub 1 denotes the larger of the two sample variances. Because the variances are never negative, neither is any F-score. Think about it. The variances are always positive because whether your standard deviation is positive or negative, when you square that number, you're going to get a positive number that comes out. So here we got a positive number divided by a positive number. That's going to yield a positive number. So there's no way any F-score can be negative. If you have a negative F-score, then something's wrong. Our subscript convention also means that F-scores are never less than 1. Think about it. If the bigger number always goes on top and the smaller number always goes on the bottom, when you take a bigger number and divide it by a smaller number, you're always going to get something greater than 1. Now, it is possible that the F-score could be equal to 1. In that event, you have equal variances between your samples. That is a very rare occurrence in the real world. Almost never happens. And so you're typically going to see one sample variance greater than the other. And so take the bigger one, put it on top. You're going to get a number greater than 1 whenever you calculate your F-score according to this equation. So if we have a test statistic that's close to 1, then that means that we have more evidence to support the claim that these sample standard deviations or variances are actually the same, that they're equal to each other. The higher the F-score value, the further apart the variances are, and therefore the less evidence we have that the variances are equal. We're going to determine p-values and critical values either with an F-table, which gets really hairy because you've got 2 degrees of freedom now, or you just use software, which is what a lot of people use now that we're in the 21st century. We can also construct confidence intervals to test claims regarding 2 standard deviations or variances. Remember, for means and standard deviations, variances, confidence intervals are just as reliable as using p-scores or critical values to evaluate hypothesis testing. So here's the general form for our confidence interval when testing a claim between 2 standard deviations or variances. This looks a lot like what we've seen before, looking at the confidence interval for standard deviation or variances. Again, because we have 2 populations, we're basing this on the F-score in the numerator and then critical values from the F distribution in the denominator. Let's look at an example that we've seen previously, but looking at it in a different way. So creativity research, going back to this study that was done where you randomly select people, put them into 2 rooms. One room has a blue background, the other has a red background, and everyone's asked to think of creative uses for a brick. We saw previously that there was a significant difference between the mean number of creative ideas that people in the blue room developed versus people in the red room. In fact, the blue room actually enhanced creativity, which was the claim, because its average number of creative ideas produced was higher than those tested in the other room. So here we see the same sample statistics that we saw previously, but now we're asked to test at the 5% significance level the claim that the standard deviation of both groups is the same. In other words, there's just as much variation between the number of ideas in one group as there is in the other. So first we form our hypotheses by representing our claim symbolically. Our claim is that the standard deviation of creativity scores for subjects in the red room is the same as the standard deviation for creativity scores for subjects in the blue room. Notice that the red room, the stats on the red room, had the higher standard deviation, which means it's going to have the higher variance, and therefore that's the group that gets the subscript 1 with all of its variables that represent its sample and respective population. The blue room is going to be represented with sigma sub 2 because it had the lower standard deviation and hence a lower variance. Thus, we're going to say that sigma 1 equals sigma 2 because we're saying that the standard deviation between both of them is the same. That there's not much variation between each of the different samples. If I divide both sides of that equation by sigma sub 2, I get what you see over on the right. Sigma sub 1 divided by sigma sub 2 equals 1. This is the algebraic equivalent way of writing our claim symbolically. The null hypothesis is always a statement of equality by definition. So mu sub 1 over mu sub 2 is going to be equal to 1. But this is what we actually claimed. So the general alternative hypothesis convention of reflecting the claim can't really be used here. We're going to have to take the opposite because all equality goes with the null hypothesis. So we have to take the opposite of the symbol that we used for our symbolic representation of our claim. Mu 1 over mu 2 does not equal 1 becomes our alternative hypothesis. Here's our test statistic. Notice I put in the values that I have from the previous sample set, punch it out, and out comes 2.371. Notice that when I set this up, the larger of the 2 numbers goes on top. Okay, so if you're actually getting an F-score test statistic that is less than 1, you did something wrong. You take that number and take the reciprocal, flip it over, because you've got the wrong number up on top. Now that we have our test statistic, we can find our p-value. We use technology to do that, and then compare it with our significance level of 5%. We find that our p-value, 0.0129, is less than 0.05. Therefore, we're inside the critical region, and we can reject H0. We will reach the same conclusion if we compare our test statistic with our critical value. So here's our F distribution. We get our critical values by putting in the area in between the tails. So that gives us our critical values. Then our test statistic, 2.371, is actually over here in the right tail. It's greater than this rightmost critical value, 1.968. So therefore, we're inside the critical region, and we reject H0. So either way, there is sufficient evidence to warrant rejection of the claim that the standard deviation of both test groups are the same. If we use a confidence interval, we can reach the same conclusion. So I set this up first by finding my F values, which we just did on the previous slide. So these are the critical values that come out of my F distribution. So here's F sub alpha over 2. Here's F sub 1 minus alpha over 2. And then I substitute these values into the general form. So here's my general form. Notice that the F score that we calculated previously is on top. So S sub 1 squared over S sub 2 squared is simply the F score. So when I calculate this out, I don't have to redivide the variances. I just go ahead and just take the F score and put it in, 2.371. And then the critical values from the F distribution, you can see I put them in, punch all this out on the calculator, and out comes 1.2 to 4.68. This then is my confidence interval. Now, because 0 is not included in this confidence interval, that means there's definitely a difference between the standard deviations of each testing group. Furthermore, because all the confidence interval values are positive, that means that the variation in the first group is going to be greater than the variation in the second group. So the standard deviation for group 1, which was the red room, is going to be greater than the variation from those who were tested in the blue room. This actually matches up well with the conclusion we reached in an earlier lecture, where we were looking at the mean values for each of the groups, the number of creative ideas they each produce, and it was shown that the blue room actually produced, on average, more creative ideas than the red room. So that's not surprising to find that those in the red room had much more variation, because again, the ultimate claim being made was that blue enhances creativity. So if you don't have the blue, you don't have the creativity, and it's just a free-for-all. So it's kind of whoever you get to put in there. That's what comes out. But with the blue enhancing the creativity, you get a much tighter spread on the data. So the data is more close together, the number of ideas that people produce, because you have the enhancement of the blue with the creativity. So that actually pairs up really well with what we've seen previously. We have alternative approaches to testing claims that are not as sensitive to normality. So again, the F test is really sensitive. The underlying populations must be normal. So another way that statisticians like to say this is that the F test is not robust against departures from normality. It's very sensitive to those changes. So if you want to use a method that's not so sensitive to normality, there are some out there. One that you will be asked about on your homework assignment is the Count 5 method. So essentially with the Count 5 method, you have to have both sample sizes equal to each other. Okay, so you can't have different sample sizes. You have to have the same sample size for each one. And then for each of the samples, what you have to do is you have to take what's called the mean absolute deviations for each of your sample sizes. And then you just pick the sample with the 5 largest mean absolute deviations, and the population that is represented by that sample is then concluded to have the larger variance. Now, mean absolute deviation means you take the individual data value, subtract out the mean from that sample, then take the absolute value of that difference. That's the mean absolute deviation. You can do this for each of the data points in each data set. So this sample mean x bar is going to be different depending upon which sample you're working with. But you're going to calculate this value out for each one of the data values in your set, pick out the 5 largest ones, and if all 5 of the largest ones are in the same data set, then that means that the population represented by that data set has the larger variance. If you don't get the largest 5 within the same data set, then you're pretty much concluding that the variances are more or less the same. Pretty simple method, a little computation heavy, but we're living in the 21st century. We have computers do all that for us now. So there is ways to actually automate this sort of thing, especially if you use a spreadsheet program like Excel. And that brings us to the end of this lecture. Again, if you have any questions, you know where to find me. Otherwise, I will see you in class. Thanks for watching.